It's our pleasure to have Michael Tretyakov from Nottingham. He will be talking about geometric numerical methods for confined Langevin dynamics.
Thank you for giving an opportunity to give a talk here at Newton Institute. So the talk is about numerical methods for Langevin equations in bounded domains. And within the talk, what I will understand under the word Langevin is what is also called underdamped Langevin dynamics or kinetic Langevin dynamics. What is called within the statistical community as Langevin dynamics, I will call either overdamped Langevin dynamics or Brownian dynamics or just stochastic gradient system. The talk is based on a recent joint work with Ben Leimkuhler and Akash Sharma, and Akash is here in the audience. Plan is as follows. I will start with motivation, though motivation is not really needed much following the workshop we had last week, and then I will try to put this confined Langevin dynamics, so Langevin dynamics living in bounded domains, within a broader context by starting first with a reminder about Langevin equations in the whole space, and then also providing a brief link to stochastic gradient systems with reflection. The main objective of the work, which is on arXiv, was on constructing numerical methods, and we'll start with first order numerical methods for this object. We'll show some theoretical results showing their weak sense convergence at finite time and also for computing ergodic limits, and we'll look at numerical methods which show second order behavior in contradiction to what we usually expect. Our intuition built from the stochastic numerics over all the years, and we will provide a justification why those methods are of second order. If I will have time at the end, I will show a couple of numerical experiments out of many we have done. So the first motivation comes from the question how to sample from distributions with compact support. The typical objects, underdamped, overdamped Langevin equations, are sampled from domains without boundaries, unbounded domains, full Euclidean space. While putting SDs in the bounded domain should give us a possibility to use them to sample from distributions in compact support. The object which we'll be looking is quite physical in terms of having the right physical behavior on the boundary, and then it's suitable for molecular dynamics applications. The papers by the group of Bassi, which I will cite later, they exploited this object, extensions of this object within computational fluid dynamics. It can be used within constraint optimization, and also, as it is usual, we can link our stochastic differential equations via Feynman-Katz formula to PD problem, and on this occasion CLD equations, they serve as stochastic characteristics for linear parabolic PDEs with specular boundary conditions, and if we can solve those SDs combined with the Monte Carlo method, then we can numerically solve the corresponding PDEs as well. So let me start with a very brief reminder about Langevin equations in the whole space. And here it's in its simplest form that we have constant friction and we have constant diffusion according to fluctuation dissipation theorem. We also can write it as a formally as second order differential equations, and under some conditions on the potential U, the system is ergodic with invariant measure being Gibson. Since it's the usual Langevin equation, I would stress that Q lives in the whole Euclidean space here. Langevin equations have some structural properties. The first to discuss is that if you remove this friction term here, then the remaining system will be Hamiltonian system with additive noise. If you put gamma to 0, then it is deterministic Hamiltonian system. From deterministic analysis, known for quite a long time, from stochastic numerical analysis, also known now for a while, that if you take a Hamiltonian system and if you want to simulate it over a long period of time, then the methods of choice are so-called symplectic integrators, corresponding to the fact that Hamiltonian systems are characterized by preserving symplectic structure. And symplectic integrator means a numerical method which preserves symplectic structure at every step. Langevin equations, of course, do not preserve symplectic structure, but when our gamma is relatively small, this object is close to a Hamiltonian system. Then it's natural to put a requirement on numerical methods that when Langevin equations degenerate to a Hamiltonian system, then our numerical method for Langevin equations should degenerate to the corresponding symplectic integrator. The other property of Langevin equations is the phase volume contraction. So we have the Jacobian and this rate of contraction. And since it's another structural property of the continuous dynamics, it might be beneficial to preserve it within numerical integrators, more precisely to contract the phase volume at every step with exactly this rate. Such methods sometimes called quasi-symplectic or something similar to that. To construct methods which satisfy these two requirements, and more or less all methods which are used now in practice, explicit methods, they're based on some kind of splitting. Yeah. So this is yeah. So this is phase flow. So what we do, we have initial domain, bounded domain, and then we map this domain using the solution of stochastic differential equation, getting a new domain dt. So it's a map using the flow. We have the set of initial conditions as a domain, and then we map this flow. Yeah. This is a D. Yes, that's a D. Yes, it is the whole space. Yes. We haven't switched to bounded domain yet. So here, so explicit methods which satisfy these conditions, and more or less all methods which are used for sampling or for molecular dynamics are of that type which I was describing, and we use one or another splitting arrangements to construct such explicit methods. This is a particular splitting of the original flow. Other splittings are possible to construct other methods. I'm concentrating on this splitting because the methods which we will later on see, they will rest on this splitting. So the flow split here in Einstein-Uhlenbeck process, which we can solve exactly, of course. This is the free particle movement we can solve exactly, and we can solve exactly propagation of velocity according to the potential with fixed Q. Then the construction of the methods works as a concatenation of those exact solutions in a certain way and getting a variety of integrators. There are a lot of papers, probably thousands of papers studying the methods. In particular, I mentioned here works by Charlie and Ben, where they studied variety of splittings and comparing them, but there are a lot of more papers on that. So now we arrive at the first object we will be considering. On the next slide, there will be a particular case of this object, and both will appear within the slides. So this is confined Langevin dynamics, or Langevin dynamics living in a bounded domain. If I remove this red term, then we are back to Langevin type dynamics in the whole space. what this red term does, it keeps the position of the particles in this bounded domain G, this boundary partial G, and G is the normal vector. I think it should be outward, and Ig is the indicator function. So what this term IT does, if you look at the structure here, it works only when our trajectory hits the boundary, and if it is the domain, the configurational domains or domains for Q, then what happens with the velocity at the time of collision of the particle with the boundary is that the normal part of the velocity, so you see that we are computing here the normal part of the velocity, changes its direction on the opposite, while the tangential part stays the same. If you think in terms of how Q evolves, I will do it schematically because Q, of course, is random, then we will approach boundary at some angle alpha, and we will reflect back the same angle from the opposite side. This is so-called elastic collision, where energy, kinetic energy, is not lost; it is conserved at the collision time. And also, solution of this system is Q and P, because R is fully determined by Q and P. There are very little number of papers on that object, though physically it looks very nice. It essentially describes that if I throw a ball at a hard wall at a certain angle, this ball coming back at the same angle. Very natural physical object. But there is not much study of it in terms of stochastic analysis. There is not much study in terms of properties of the corresponding PDEs, and not much done numerically either. So the numerical works we are aware of is these papers by the group of Bassi and Mafti theses, and their methods proposed were only first in 1D and then in half space. So they didn't work with curved domain, and also their first order method is of different type than the one we are suggesting here. The second object is just a particular case of the previous one. We obviously want to sample, so then we take the drift B in the usual form for Langevin equations. We take sigma in the usual form. Without red term, again, we have the usual Langevin equations. This red term keeps it inside. If we put some assumptions on the boundary and on the potential, then the system is ergodic with the invariant density. And the invariant density has exactly the same form as for usual Langevin equations, but with the important difference that this Q now lives in bounded domain. So then, if we can simulate this object well, we can sample from distributions with compact support given on this G bar.
So no condition on the gradient.
At the boundary, no. On the boundary, no. No, it should, if it's sufficiently smooth, it's okay. No. So let me compare briefly CLD with reflected SDs, which you will see can do a similar job. So this is overdamped reflected Langevin equation. So that's the usual Langevin. Then we can keep trajectories inside using the local time, and under smooth, again, assumptions on the, or whatever suitable assumptions on the boundary and on the potential, it has invariant measure, but again, X now, in contrast to the usual overdamped Langevin dynamics, belongs to the domain G thanks to the local time. And as you see that this invariant measure is just a marginal for the invariant measure we have for the ECLD. So this object also can be used for sampling from distributions with compact support. And indeed, this was the topic of our previous paper with Ben and Akash. What I can say more here, using the cited papers here, that the same result which is true for Langevin equations in the whole space, which I think was proved first by Nelson back in 1970s, that the position part of the Langevin dynamics converges to the solution of the overdamped Langevin dynamics when friction goes to infinity. And this is also true for this reflected object, so this connection in terms of distribution. So let me show a little bit more on comparison, showing the trajectory. So first, the trajectory of the reflected CLD. So we expect from overdamped Langevin, it's a bit rough, but also it's not physical in terms of reflection. Whatever angle you come at the boundary, it comes back at you along the normal. We could have replaced normal with an oblique direction, but it will be still the same oblique direction at which it will be coming back. In comparison with CLD, where this reflection is very natural. So here it will be CLD trajectory for 2 degrees of freedom. So I will plot only configurational space. The whole system is of course four-dimensional, and we will see that, well, trajectories as you expect smooth, and when we hit the boundary, then they are reflecting at the same opposite angle as we expect it to happen. And the next video is the following. So it is 1 degree of freedom, but I will be plotting the phase space. So I'll be plotting P and Q, and the aim here is to show how the momentum changes, how this boundary can, how this collision with the boundary works. The boundary is at -1. On the x-axis, we will have position. On the y-axis, we will have momentum. And you see when we collide, then the velocity just changes the sign from minus to plus. Because it's one-dimensional, here no tangential part, it's just changing the sign. So this shows that obviously, well, it was shown, you could observe this from the system itself, that on the boundary our velocity jumps. It's not a continuous process on the boundary. So next we write down backward Kolmogorov equation, to which we connect our CLD via the Feynman-Katz formula. The equation itself is as usual, nothing really different here. Terminal condition, but we also have specular boundary condition here. Yeah, we are working in a boundary domain. So when Q belongs to the boundary, then this condition should be satisfied. And the structure of this condition is again the same as this R term we had in CLD. We will need assumptions on smoothness. Again, our purpose is to design methods, not looking for optimal assumptions. So we need smooth boundary. We need, in the finite time convergence, we need that this coefficient sufficiently smooth, globally Lipschitz in P. We need smooth test functions, and we also need some assumptions on smoothness of the solution to the Kolmogorov equation. In terms of the case of ECLD, when we choose this B as force and friction, then it can be shown that the solution is exponentially ergodic, and phi bar within the talk will be the corresponding ergodic limit, which we'll aim to simulate. We can write down the Fokker-Planck equation. Again, equation itself is as usual, but it is complemented by the specular boundary condition, and it's straightforward to check that Gibbs density satisfies this boundary condition, and obviously satisfies the equation as usual. So this confirms again this setting that we can use this ECLD for sampling from bounded domain if you manage to solve the object numerically. To prove convergence to ergodic limit, we also need assumption on decay, the usual assumption on decay of Kolmogorov equations, solution of the Kolmogorov equation with time. So now we will construct numerical methods. I'm recalling the system for which we construct. So first, for kind of generic setting of numerical methods, we have B here. We are working with uniform discretization of time. And inside the domain, when we are not experiencing collision with the boundary, this is just usual SD, and we can approximate it by whatever favorite scheme we have. So then the whole construction of numerical method concentrates on what to do when we are close to the boundary and we can cross it. So that's the main element of the construction. And we are doing it in the following way. And this way is guided by the structure of this red term R. So we assume that our current state is this QP small, and we want, before kind of possible collision, and we want to find the next step, what happens after that. And we do this trial. So we have our position, we have our momenta, and we propagate Q over time step H accordingly. So if my Q is here, I propagate getting Q plus pH. And if my new state, which is here, will be denoted as Q1, is inside, I don't need to do anything. It's all fine. Now, if I'm in the situation that Q is somewhere here and the velocity or momentum is forcing me out, so this will be my kind of, I don't think we have notation here, so I'll just write Q plus HP. Then I need to do something about it. And doing something about it means the following. So we find the intersection, we denote as QC. And by finding the intersection, we also finding then the corresponding random time, typically random, where we intersect. Then we change the direction, the normal direction of the velocity, and using this new velocity, we continue from this point, will be QC plus H minus tau P1. And this will be our new Q1. So it's very kind of natural, elastic construction for this collision. And the whole procedure is denoted as AC. In order not to write.
Also not in the domain, like something.
Yeah, so in the case when it is half space, that's not possible within our construction in comparison with construction which used by analysis before. But in the case of curved, it's possible. Then one way is to do it iteratively. And we have an argument that the number of those possibilities is finite. A smooth thing. So that's one possibility. What we did in numerical experiments, we just rejected those things. And well, Akash is here. He might remember how often this was happening on trajectories, but it was very rare. So yeah, this was kind of important consideration. Of course, not only on the curvature, also on the time step. Yeah, because you're close. Yeah, so the smaller the time step, the less curvature you feel.
It was also your first step. You jump over some boundary and then land.
Yes. Well, yeah. Yeah, no, you can choose the initial step so that you're running out immediately because, yeah, of course. So we are aiming at constructing first order schemes, and for just simplicity we are taking that the vector field for P is approximated using Euler approximation. First order scheme means we need to match 3 first moments. We can take, just for simplicity, standard normal distribution, or plus minus 1 is probability 1/2. And we essentially constructed the numerical method, so it's a text written, but it's probably easier to look at the table. So we do this, in this scheme, we do first the trial for the momenta, so we update it according to the Euler scheme, and then we do this AC step, or we can do the other way around. So it's there sort of conjugate the schemes one to another. These schemes, and also the schemes we will see later, this second order schemes, have this nice property that they do preserve this physical conservation of the energy at the collision, so of the kinetic energy at the collision, so that the momenta is preserved. And this property is actually important in some parts of the proof we do. We prove the following 2 theorems for the first order scheme. So the first one is finite time convergence scheme. EAC might depend on the integration time, and we have the second theorem for the ergodic limits. EAC can't depend, of course, on T capital. The pathways to proofs of both theorems is roughly the same. I will show the idea of the proof of the first theorem. Second would be similar, a little bit more involved, because we need to care about the constant being independent of integration time. So the proof, well, first we prove that moments are bounded, which is not a surprise here, working in global Lipschitz setting. And then we prove the one-step lemma, which has interesting features. So the proof we use for the convergence is resting on rewriting the global error in a telescopic sum of one-step errors in which we explored this backward Kolmogorov equation solution. And essentially what we have here is one of those terms from the telescopic sum. It's the usual analysis of weak convergence for numerical schemes. Inside the domain, we are working using the Euler scheme on a single step. It's of weak order 2, so that's h squared where it's coming from. But the collision we are doing is very rough. It's of order 1. And then we have this term here, and you see that this relates to collision because we have indicator function here that we went outside. So let me step back here and mention that the way we are constructing collision here is the same as it was done in molecular dynamics when they consider Hamiltonian systems in bounded domains. And it is known from deterministic analysis as well that the order of this collision is h. So of course, this h square I do of order 1 over h steps, so this will give me global order h. But here I need really carefully consider the sum of those expectations. Otherwise I will not get convergence. And as you expect, then the next lemma is the critical lemma for the proof of first order convergence, that the sum of those things which are prefactored h is bounded by a constant which is independent of h. So the form what we need to prove is dictated by the expansion, but to see what the meaning of this lemma, we can just remove this long term, which is technical, and see that we are just summing the number of times we collide with the wall. So what we are estimating here, that average number of steps on which we experience this behavior is bounded by a constant which doesn't depend on the time step. And then, of course, we sum everything up, and we are getting first order. To prove this lemma, we use the following constructions. We write down the associated boundary value problem. So T here is the one-step transition operator. And this boundary value problem has this solution. And the solution is of the form we need. We just need to write G here to get the expression which is in the lemma, this long expression, and then it will be exactly the V small we had here. So if I choose G of that type of form, then I will connect the two objects. Then what we do next, and this is the most trickiest part of this proof, is we need to find a sort of a Lyapunov function which solves this problem with some G, so that this G is bigger than what we need, and then we estimate V by this V capital. And if I know V capital explicitly, that's easy job to do. I'll not show all the elements, but I'll show what type of V we have chosen on this occasion, which works, and then some long calculations which gives us eventually the right estimates and the proof. So now we are coming to second order schemes. We are looking at them only in this situation, of course, when we have force and friction. And since we are working at the second order schemes, I need 5 moments to be matched, but we can assume we are just working with standard normal distribution. And also, for simplicity of how the methods will be written, I introduce this solution to Ornstein-Uhlenbeck SD, which we had at the beginning as a part of a splitting over time step h. So this will mean O big. And we constructed a few methods. So 3 of them are here. There are 3 more mentioned in the paper. So let us look how they work. So I will concentrate just on this method, and the rest will be just different concatenations. So we do half step of Ornstein-Uhlenbeck, then we do half step with the force, then we do our collision step. So either we stay inside the domain, then we just do the usual step for Q, not changing P, otherwise we are working with this construction, and then we do the symmetric stuff. So this method, as I'm sure all of you know, in the whole space, in the Euclidean space, gives a second order. Now here we come to a sort of contradiction that if I switch noise and friction off, so if I put gamma equal to 0, my system obviously becomes a Hamiltonian system with reflection, for which this method will degenerate to a numerical method of order 1. So this is proven in the deterministic case, tested in the deterministic case. It appears, for instance, in Ben Leimkuhler books and in his papers too. However, here a miracle happens that this method becomes of second order. If you look carefully on the analysis of the deterministic method, and again it's noted by others as well, that if this tau which we had here is exactly, so the tau which is sort of moving from this Q to this QC, this tau is exactly at half step. If it's exactly equal to h half, then this method in the deterministic case of second order. But in practice, when you run Hamiltonian dynamics, this actually will never happen. And obviously, it can't happen in the stochastic case either. So this was kind of puzzling observation for us. And what we tried to do, so we observed, all 3 of us ran a lot of detailed, very careful experiments and saw that order is 2 rather than 1. And next would be justification of second order in the case when we're working with half space. So the boundary here is hyperplane with the first coordinate being equal to 0. In this case, the collision part is very easy because collision happens when this Q1 goes negative, the first coordinate of the position. I can compute tau exactly. my new P is just changing the sign of the first coordinate in P. So that makes life easier because we can write everything explicit. And we proved the following lemma, which is a bit unusual for one-step lemma in terms of formulation, but also in terms of proof. Formulation is a bit unusual because I assume that the point is random and I'm averaging over it here as well, the point at which I start. And the error looks like that. Not a surprise to see h cubed here because in the main part of the domain, outside the boundary, outside this collisions happening, the scheme is of global second order. So then weak order on one step should be cube. And we have here h squared instead of h. And that's kind of the main part of this justification, that we got h squared. So based on this lemma, then we can prove second order convergence by the same argument. So this will become h squared, and the number of those is independent of h, and we will be done. So why it works in the stochastic case? It turns out that this tau is not equal to h half, but on average it's very close to h half, up to terms of higher order. And that gives the reason why we are having second order convergence. So the proof starts with very careful rewriting of one-step error. And one of the reasons why we need very careful rewriting, that backward Kolmogorov solution can't be smooth when our position is on the boundary because we have jump of the velocity. So then we need to arrive in this expansion so that we can use the boundary condition and switch from P3 to P2. But that's kind of more or less the usual stuff, and we expand all these errors carefully, and eventually we arrive at this expression. So R1 and R2 are in the right form, but these terms, if we do nothing with them further, they are of order h. Because, well, tau is of order h. This can be considered bounded. So we need to work carefully, but you see from the structure that if tau is exactly h half, they disappear. So then what we do next, so we modify this a bit for the analysis, because P2 and P3, there is one-to-one correspondence between them. We can get rid of that, and I can move Q0 to QC because they're close enough. And next, for the illustration, I will do the following. So I will first look at term tau multiplied by this bracket, and I will only consider the first component, P31 multiplied by the derivative of u with respect to first component. Similarly here, other terms can be treated in the same way. And the second term which we'll be looking at is h half multiplied by this expression. So we start with the first one. So this is my first term. This is tau P3. And then I can replace tau P31 with Q01 because this is how tau is computed when we work with half space. And in order not to carry on all this long expression, I just denote it as V1. Next, in the half space situation, these two events are the same. And then we can just do the integration. I can just write this expectation at this integral. Because of the indicator function I have, I apply Taylor expansion here, and then I get this remainder R1. I'm skipping a bit details, but that's the sense of it. So we get this long integral and some terms of higher order. And as you probably already guessed, the other term, doing the same stuff, we arrive at exactly the same expression plus term of higher order. And then we are getting the right order. So that's the justification for the second order schemes. I have actually time to show some experiments. So we've done experiments in finite time, for finite time convergence. So we are using usual Monte Carlo estimator for expectations. So we had this model, and we constructed some models for the CLD for which we can write the solution exactly analytically, so that we can test finite time convergence without being abstracted by not knowing exactly the reference solution. And we see that second order schemes are exactly on the line. And the other method we have done, so that's tables as well. So this, which I'm presenting, the other numerical experiments in the paper, is for quadratic potential. We tested 6 of those methods. Some of them more accurate in terms of the constant, but they're exactly all of second order. So this is for computing ergodic limits. And we have done experiments in curve domains and so on. So this is all showing always the same type of convergence. So in terms of the summary, if I may, maybe this talk will move some of you to work on this object, which is very unstudied in many ways. So there are a lot of interesting things can be done. So further theoretical analysis of the second order integrators can be done. More can be done in terms of existence, uniqueness, ergodicity, corresponding PD problems, their properties. Obviously, other methods can be constructed. And more numerical tests can be done. For instance, we have not done the test comparing what would be benefit or difference, probably the same as in the Euclidean space, but we haven't still done it, to compare CLD with RCAD for the sampling purposes. What will be the difference between the two? Thank you.
Questions?
Finite time horizon case.
Mm-hmm.
Fixed time. You have this constant C.
Yes.
Usually this C grows exponentially.
Yes.
And then so maybe I missed if you said something about the ergodic case. So in ergodic case you need to get around that.
Yeah, in ergodic. Yeah, in the ergodic.
Your domain G is sometimes not bounded.
So for the yeah, so for the theorems, we assumed that G is bounded with a nice boundary. So we don't. It's a compact, yeah. So we don't need any assumption on U.
Okay.
Of course, this can be generalized when it is half space, and then we need condition on U. Yeah. Yes. Well, I think that condition on U would be the same as conditions used in the whole space. I don't think it will be any different.
It's always a question of whether you're globally strong or whether you're going to sort of have only at infinity.
No, I think so. In the papers of Bassi, they concentrated on half space, though it's on Makin-Lasser version of that. But with the right conditions on the drift, it always will be. I think they were very strong on the drift. They assume bounded drift. But the usual Lyapunov condition should work. Yeah, well, it needs, so there is no result on that. So this is one of the things I'm trying to say, that there are a lot of the object is so natural, it's not kind of made up object, but there is no. So what I think that if you have boundary here, you can have a drift which basically keep you in this domain rather than pushing towards the boundary. Yeah, so one-sided Lifshitz condition of whatever type should do the same job, because there is no really, on intuitive level, difference between whole space and this if the domain is unbounded. Unless you start creating kind of wedges or something like that, where the process will stuck and so on. But if the domain is relatively nice, so I would think that the same assumptions as we use for reflected SDs, that either the boundary is smooth and then we can do whatever we want. We don't need, we do not assume that the domain is convex, so domain is not. But if you start losing smoothness of the domain, then we need convexity. This is how it usually works for reflected SD. I expect something similar might happen here as well. But you're right in terms of interesting questions. And further study both of the object and numerical methods are definitely of interest. When we're in the bounded domain, we can do whatever we want. We can create absolutely crazy potentials, right? Which can go, yeah.
So just one question. Maybe you referred to that at some point, and I didn't get it. Would you lose on the thing that you wrote on the board, for example, on the first scheme that you wrote on the board, where you calculate the time that you hit the boundary and then you reflect for the rest of the time? Would you lose a lot if you would just assume that this time is h/2 and just do that all the time, so that you don't have to compute the time to hit the boundary? Would it be a big
you mean the
approximation error if you were to do that? Always take epsilon h.
You need to know where to reflect.
yeah, so the
You know that you reflect between
the trouble will be, so I don't know how to prove this, because on the boundary we have the condition, say for backward Kolmogorov equation, that when they reflect, then at this point the velocity should equal me 2 things. Yeah, so if the problem that velocity is not continuous, it jumps. And then in the proof you need to accommodate for that. If you start jumping inside the domain, I don't know, maybe you can create approximate, yeah, so
right.
so maybe it would be doable, but the proof would be quite different. But I sort of doubt. Well, physically it's certainly not right, because you want to collide with the true wall.
Sometimes people sort of put a very strong push. I mean, not in this context, right? You put a very strong push and you go up.
Yeah.
You try to do this thing here also.
Yeah, of course you can. So the same in the overdamped Langevin, that instead of doing reflection, you can put huge barrier there. But this is not nice numerically, because you put in a strong thing, then you need to work with a small time step or something. So you need to work with stability. But here's both objects, reflected SD, which we looked before, and this one replaces, in effect, this artificial potential which people create so that you don't go there. And here also you maintain exactly what is your domain, right? You don't need to extend coefficients, nothing, so you just work there. But that's a counterparty to what other people do in molecular dynamics and statistics as well. And this looks more natural and nice, I think, in terms of integration and numerical integration and construction. Especially in high-dimensional domain, you need to start creating how these barriers should go up and so that.
Computational complexity is also interesting.
Yeah. Also here, what we can do is that, so if you imagine the potential, my potential kind of global minimums can be somewhere there. Yeah. So if you have a barrier, you can't put it kind of natural way here. So for this sort of problems, at least I believe this is more natural object. Computationally, yeah, one can compare when and how it's beneficial in comparison with artificial potentials.
Here you need to solve some equation.
Yes. Yeah, you need, yes.
This will be reflected.
Yes, of course, yeah. You need to solve, well, if it is a curved area, yeah. Some optimization problem.
many times you spend.
Yeah. Well, here, the benefit, what I would consider, we didn't do this computational comparison, that when you work with reflected SD, then the number of collisions is proportional to 1 over square root of h. So there is more there, and here it's finite. So this complexity is at play here as well in terms of Langevin equations. So we have P. So yeah, fair comparison, something which can be done.
Any final question? We can thank the speaker again.